Hi everybody, hope you're having a great day. Today we're going to learn about electrons and light. So remember that we said that quantum theory states that electrons have a dual nature. That means they have two natures. They behave like particles since they have mass and speed, which are properties of particles. They're considered particles, but also they are considered waves as well. And so we're going to start by taking a look at some properties of waves. And you've probably studied this in physical science your freshman year as well. So the first property of waves we're going to look at is wavelength. So the symbol for wavelength is lambda. It's the Greek letter lambda. It sounds like an L. But it's written, looks kind of like a fancy upside down Y. So the wavelength is the distance between identical points on successive waves. So that would be the distance between crest and crest, or the distance between trough and trough. So there's your wavelength here, and there's your wavelength here. And so if you compare, let's call this wave A and this wave B. Wave A would have a long or longer wavelength. Wave B would have a short or shorter wavelength. Now, wavelength is, from its name, a length, and so we use length or distance units to describe wavelength. So wavelength could be measured in meters, or nanometers, or any other distance units. Typically nanometers, since this is, a wavelength of light, and so it's very, very small. Next property is amplitude. Amplitude, the symbol for that is capital A. We're not really going to talk much about amplitude in chemistry, but amplitude is the vertical distance from midline of a wave to the peak or the trough. So the amplitude would be like from right here in the middle all the way to the top, or from the middle all the way down to the bottom. This again is a distance, and so again the units would be either meters or nanometers or any other distance units. Next, we're going to talk about frequency. So frequency gets a symbol nu. I know it looks like a V, but it's actually pronounced nu, N-U. This is the Greek letter that sounds like an N, but again, it kind of looks like a fancy V when we write it. So frequency is the number of waves that pass through a particular point in 1 second. So it's the number of waves per second. And so for the units for frequency, it would be number of waves, so that's just a number, no units, per second. So the units would be per second, which is 1/second. You can write it this way, or you can write it as seconds to the -1. That's the same thing. That is equal to 1/second. Or you can write it as capital H lowercase z, and that's pronounced as hertz. That's short for hertz, H-E-R-T-Z. Hertz was a physicist that worked on light waves, and so they named frequency after him. So like we said, frequency is the number of waves per second. So let's look back at wave A and wave B. If you look at both waves, these are light waves, so they travel at the speed of light, which is a constant, so they both have the same speed. So they travel the same distance over time. However, if you look at this has a lot more waves in the same distance. And so per second, this would have a much higher frequency than this wave. So we can say that wave B has higher frequency, wave A has lower frequency. So based on that, you can tell that the relationship between frequency and wavelength is an inverse relationship. As you increase one, you decrease the other, and vice versa. There is a mathematical equation that describes that relationship. It's right here. C is equal to lambda nu. C is the speed of light, and it is equal to 3.00 times 10 to the 8th meters per second. So that is a constant. It never changes. And you don't have to worry about memorizing this number. This will be given to you on a test. You do need, however, to memorize the equation and recognize all the symbols in it and be able to use it. So again, C is the speed of light. It's a constant. Lambda is wavelength. And if you're going to use 3.00 times 10 to the 8th meters per second, then your wavelength in this case would have to be in meters. And then nu, that would be your frequency. Now, if you can't tell by looking at these waves, the inverse relationship, or if you forget and yet you remember the equation, then you can, from the equation, figure out that it is an inverse relationship. The way that you would do that is, if you write this equation, just plug in any easy numbers. So, for example, I'm going to say 4 is equal to 2 times 2. Don't worry about the units for now. We're just looking at the relationship between the two variables. So, in this equation, C equals lambda nu. C is a constant. It never changes. So that 4 will always be the same. So let's put in a 4 here. And now let's increase our wavelength. So let's make it go from 2 to 4. What would have to happen to your nu, or to your frequency? In order for the constant to stay as 4, then this number has to go down to 1. So as you increased your wavelength, you decreased your frequency. So that would be an inverse relationship. So again, just plug in any numbers, any easy numbers for you on the test if you get stuck. Another equation that you need to know is E is equal to H nu, right here. E is energy. The units for energy is joules, and the symbol for that is capital J. H is another constant. It's called Planck's constant. Planck is another scientist that they wanted to name the constant after him to honor him. And it is equal to 6.626 times 10 to the negative 34th joules times second. Again, you don't have to worry about memorizing this number. That would be given to you on a test. But you do need to know the equation and be able to use it. So I want you to kind of look back at wave A and wave B. Think about the energy of both. Which one do you think has more energy? Maybe imagine yourself like standing in maybe like an ocean, and imagine that these are water waves coming at you. Which one do you think would hit you harder? Probably wave B. You probably don't want to be standing right here with wave B hitting you. You'd probably be better off standing, in front of wave A. So wave A has lower energy. Wave B has higher energy. Now, if that doesn't make any sense to you, if you can't visualize that, or you just don't like it, then just look at the equation E equals H nu. So if you look at the relationship between energy and frequency, if you look at your waves, A and B, we said this is lower frequency, so this is lower energy, so it's a direct relationship. Let's prove that here. So again, just plug in any random numbers. Let's go with 4 is equal to 2 times 2 again. Okay? Now, E equals H nu. H now is your constant, so that's the number that never changes. So let's keep that as a 2. And now let's increase our energy. Let's make that maybe an 8. So now, what does the frequency have to do? It has to increase to 4. So as you increase your energy, you increase your frequency. So that is a direct relationship. Okay? Now what if I ask you, what is the relationship between wavelength and energy? Is it direct or is it an inverse relationship? if you look at waves A and B, this has the long wavelength and it has the lower energy. So that looks like an inverse relationship. Now again, if you can't visualize that or it doesn't make sense to you, look at the equations. So if we look at the equation here, let's say you increase your energy. The relationship between energy and frequency is direct. So if you increase your energy, you increase your frequency. Okay, so increase energy, increase frequency. Now let's look at this equation. If you were to increase the frequency, what would happen to the lambda? It's an inverse relationship, so it would decrease. So an increased frequency would cause a decrease in lambda. So that means that the relationship between energy and wavelength is an inverse. You increase one of them, you decrease the other. So you need to be able to use these equations, these two equations here. You need to know the symbols for each of the variables, be able to use them and know the relationship between lambda and nu, E and nu, and then E and lambda. Maxwell proposed in 1873 that visible light consists of electromagnetic waves. And so electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. So remember that we said energy or light is emitted or absorbed in discrete amounts or quanta or quantum. So we said that it's called quantum theory because the electrons have discrete amounts or quantized amounts of energy. They could be set amounts, one set amount or another set amount, but never in between. So basically Maxwell said that light is made up of these electromagnetic waves or electromagnetic radiation. So that's where we get our electromagnetic spectrum here. So the visible region in the electromagnetic spectrum is a pretty small region. You do need to know the colors, Roy G. Biv. So these are the colors of the visible light. You need to know that before that there's infrared, after that there's UV. There are other electromagnetic radiations as well, like X-rays, gamma rays, microwaves, radio waves. And so usually infrared and microwaves, so things that are before the red, those you can usually feel them as heat. The ones above the violet, typically you can't even feel those. And then of course the ones in the visible region, you can see those. You need to also know that the red end of the spectrum is where you have longer wavelengths. The violet end of the spectrum, that's where you have the shorter wavelength. And so remember that wavelength and frequency are inversely related. And so if you have short wavelength like the violet, you'd have high frequency. If you have long wavelength like the red, you'd have low frequency. So let's just write that down also so we have it here. So these are long wavelength, these are short wavelength. So this is low frequency, this is high frequency. And then also remember that energy and frequency are directly related. And so this would have low energy, this would have high energy. Now the way that I actually remember all this is that, infra means below, ultra means above, and so they're always talking about energy here. So ultraviolet means above violet, so that's high energy, above in energy. So that means that this end of the spectrum is high in energy. And then infra means below, so that means this end of the spectrum is low in energy. From the energy, I can figure out the frequency, and from the frequency, I can figure out the wavelength. We also said that light energy is emitted or absorbed in discrete amounts or quanta. So, when we look at a light, like for example a white light, we know that white is made up of all the colors of the rainbow. But with our naked eyes, we can't really see those set colors. We just see, the addition of all of them together as white light. If you were to use a prism or a diffraction grating, like I know that you've probably used the diffraction glasses. You're about to use those in a few minutes again in this class. But if you look at a white light with diffraction glasses, you would actually see all the different colors of the rainbows. And if you look at an emission spectrum, you would actually see discrete set lines of different colors as opposed to just all of them added together. We can't really separate those with our naked eyes. So we're going to look at that in a few minutes. De Broglie is another scientist that you need to know about. He was the one that suggested that electrons behave like waves. So up until his time, we thought electrons behave like particles. But now we believe that they behave like particles in waves. Again, the dual nature of electrons. We also know, based on quantum theory, that electrons have specific or quantized energy values. So they have a certain amount of energy. Let's look at this diagram here. This is showing emission and absorption of energy. So let's say you have an element and it's in its lowest energy state, so it's in its stable, regular, low energy state. We call that the ground state. So that's when you have electrons in their lowest energy levels. And so, maybe you have some electrons here. And maybe that's your, let's say that's lithium, for example. So that would be its lowest energy level. You have 2 electrons in your first energy level and then 1 electron in the second energy level. That should be called the ground state because that's the lowest energy. What happens is, let's say that you shine a light on that substance, or you heat it up somehow, or if you give it some kind of energy, maybe hook it up to an electric current, or heat it with a Bunsen burner. So give it some kind of energy. Now electrons are kind of like little kids, little kids playing in the playground, and so normally they're in the playground, they're in their ground state. If you give them energy, though, in any form, whether it's heat or light or whatever, think about little kids. You give them candy, you give them energy, sugar. What do little kids do when they get sugar? They start getting excited and they jump up and down. Electrons do the same exact thing. So when electrons get energy, they jump up to higher energy levels. In order to go from low energy to higher energy levels, they absorb that energy that you give them. Okay? When they're at these higher energy levels, we call them excited, and we call this the excited state. Okay? Now, again, think about kids. You give them candy, they start jumping up and down. But then what happens after a little while? If they take a lot of sugar, they get excited for a while, they get hyper, and then they crash down. And so electrons do the same exact thing. They get excited, they jump up to higher energy levels, but that high energy level, the excited state, is not very stable. And so what happens is they drop back down to lower energy levels again. As they go from the excited state to the ground state, or from higher energy levels to lower energy levels, they emit the energy. When they emit the energy, they're basically emitting packets of energy. We call those photons of energy or photons of light. They're little pockets of light. And so that light, depending on what wavelength it has or what energy it has, will fall somewhere in the electromagnetic spectrum. So if it's in the visible region, then we're going to see that color of light depending on what wavelength it is. If it's in the IR region or the microwave region, then we're going to feel it as heat. If it's in the UV region, we're not going to feel it, but there are equipment that can actually detect those UV rays and X-rays and so on. So let's summarize that again. So electrons in their lowest energy state, that's called the ground state. If you heat them or shine a light on them or give them some kind of energy, they absorb that energy, jump to higher energy levels, which is called the excited state. The excited state is not very stable, so they don't stay there for very long. So they drop back down to lower energy levels. As they drop back down, they emit that energy in pockets of light called photons, and then that light might be in the visible spectrum, and then we can see it. So let's go back to this diagram. And so let's answer these questions together about this diagram. So again, this represents the energy levels. Remember, so this is n equals 1, n equals 2, n equals 3. N is the energy level. Remember, they get closer and closer and closer as they go farther away from the nucleus here. And so it says which of the energy changes, so which of these arrows represent or involve absorption of energy. So when electrons absorb energy, they're going to higher energy levels. So the ones that involve the absorption would be the ones that are going up. So B, C, and then F. Okay, now which ones involve emission of energy? When electrons emit energy, they're going to go down to lower energy levels. So those would be A, D, and then E. All right, next question says, of the 3 energy changes that involve the emission, so emission, that would be A, D, and E, so the blue ones. One results in the emission of blue light, one in the emission of yellow light, and one involves the emission of ultraviolet radiation. We want to match them up. So which one of A, D, and E is the blue light, which is the yellow, and which is the UV? So in order to do that, you look back at your electromagnetic spectrum. So there's your visible spectrum, the Roy G. Biv. There's your UV. There's your IR. So if you remember, this side has the long wavelength, the low frequency, and low energy. The other side has the short wavelength, the high frequency, and the high energy. So you need to know that. So let's look at the energy here. Okay, so we have 3 emission arrows. One results in UV, one results in blue, and one results in yellow. So which of these colors is the lowest energy? Yellow, blue, or UV? That would be yellow. So yellow is the lowest of the energies out of the 3 that we have. And so if you look back at this diagram, we're comparing the blue ones, so A, D, and E. Which one is releasing or emitting the least amount of energy? That would be D. Look at the arrow, it's much shorter. It's only emitting this much energy compared to this one and this one. So then D, since it has the lowest energy emission, that will correspond to the lowest energy color, so that would be yellow. So that one would be D. Okay. Now which one would have, which of the colors would have the highest energy? That would be UV. So out of the blue arrows, which one is emitting the highest energy? That would be A. It's emitting a whole bunch of energy here. So the A would correspond to the UV because it's the most energy emitted. So So that would be A. So then the blue is kind of in the middle. So that corresponds to E, which is emitting kind of a medium amount of energy compared to D and A. So that would be E. All right, so you don't have this in your notes, but what I would like you to do right now is go ahead and get some of those diffraction gratings, glasses. So I would like each student to have a pair of glasses, and go ahead and turn on the spectrometer, that black box in front of the room that has the glass tube with the hydrogen in it. Remember I had shown you that before when we were talking about atomic theory. So if you could turn off the lights, wear your glasses, and turn that on and look at that. If you could pause the video until you do that, that would be great. So hopefully now everybody has their glasses on, and the lights are off and the spectrometer is turned on. Now with your naked eyes, you should be able to see like a violet color or a purple color. So the reason why you see that color is because of what we just talked about. So the electrons and hydrogen are in the ground state initially. When you plug it in, that excites the electrons, that gives them energy. And so they jump from the ground state to the excited state by absorbing that energy. The excited state is not very stable, so they drop back down to lower energy levels. As they drop back down, they emit photons of light or pockets of light, and some of these just happen to be in the visible spectrum so we can see them. Now if you look at that light with your diffraction grating, you should actually be able to see the light split into different colors. You should be able to see a red, you should be able to see like a tealish color, you should be able to see a blue and a violet. Okay, now usually when I put these on, I can only see 3 colors, but theoretically there are 4 of them. If you see any light that looks like a rainbow, like it's a continuum, that is from the white light, either from the projector or from the windows or something like that. The lines that are individual sharp lines, those are from the hydrogen. Okay, now please take off your glasses. And if you look right here, this is sort of what it should have looked like. Again, if you saw any rainbows, those are just from the white light, but these sharp individual lines is what you should have seen. And so this, what you just saw, is called an emission spectrum, okay, versus an absorption spectrum. So an absorption spectrum, we have the electromagnetic radiation, so this is the visible region of it, the Roy G. Biv, with all the colors of the rainbow. What happens is when we plug it into the electricity, those electrons absorb the energy, and so they absorb certain amounts of energy. Remember, discrete amounts or quanta of energy. And so those black lines represent the light that was, or the energies that were absorbed by the hydrogen electrons. Now, as they go from the excited state, drop back down to lower energy levels, they emit photons of light, and so those discrete lines against the black background, those are the energies that they're emitting out as they drop back to lower energy levels, so that's called an emission spectrum. So if you look at the hydrogen spectrum, this is what you should have seen. Those are the 4 colors that you should have seen. If you look at something like neon, when I come back on Monday, I will show you neon. Look at that. It has so many other colors. Why do you think that is? That's because neon has 10 electrons versus hydrogen only has 1. And so the jumps back and forth, where you emit the energy. For hydrogen, there are only a few jumps that are in the visible region because there's only one electron. Whereas in neon, it has 10 electrons in different energy levels, and so the amount of energy that they can emit back from the excited state back down to lower energy levels is a lot more different. And so you have a lot more lines. So the purpose of these emission spectra is to basically identify different elements. So let's say that, I'm an archaeologist and I find a substance that's unknown. I don't know what it is. So I take it to the lab and analyze it. One of the things that I can analyze about it is that I can get the emission spectra of it. And so what they do is they have, all the known available elements. They get their emission spectrum. These are kind of like fingerprints. So they have a database for all the known elements. And what they do is if they find a sample of an unknown substance, they get the spectrum of it and they match it up to see what elements make up that substance. And so it's kind of cool. It's kind of like fingerprinting for elements. And it's used to identify unknown substances. All right, at this point, I would like you to wear your glasses again and turn on the spectrum for hydrogen. I know this says the Atomic Spectra Lab. We're not going to do that right now. I'm just showing you an example, kind of like it. We're going to do the Atomic Spectra Lab on Monday. So please pause the video until everybody wears their glasses and you turn on the hydrogen spectrum. All right. So looking at the hydrogen spectrum, remember the discrete set lines by themselves, those are the ones that we're looking at, not any of the continuous rainbows. So you should be able to see at least 3 of the colors. I can definitely see the red, the violet, and like a tealish color. So what you want to do is pick one of the colors that you can see. So for example, I could see a violet. So here's the color. Here are the colors of the rainbow, and these are the corresponding wavelengths for them in nanometers. So remember, red has the longer wavelength, so that's like at 700 and beyond nanometers, whereas violet has the lower or shorter wavelengths, so 400 nanometers. So I'm going to pick, for example, the violet color that I saw. Okay, so under color here, you can write this anywhere for now, anywhere that you have room in your packet there. Go ahead and write this example down. So then what I do is I'm going to look at the colors right here and estimate what wavelength is that at. So for example, I'm going to say that it's maybe 410 nanometers. Okay, see how the violet is like around 400? So I'm going to say that the color that I saw is close to 410 nanometers. So I'm going to go ahead and write 410 nanometers here. All right, you can take off your glasses now. So now we want to calculate the wavelength in meters, the frequency in hertz, and the joules, the energy in joules. So we want to calculate these. Your homework will involve some of these calculations as well as your lab on Monday, so that's why I'm doing an example here. So first, I have the wavelength in nanometers. I want to change it to meters. So remember back in chapter 3 when we did our conversions, our metric conversions. So that's what we're going to do here. So I'm going to start with what I have. So 410 nanometers. I'm going to multiply by conversion factor. On the bottom, I'm going to put nanometers. On top, I'm going to put meters because that's what I want. Comparing nanometers with meters, meters is the bigger unit, so that gets a 1. This gets 10 to some power. And then if you compare them, meters is the base, so that's 10 to the 0. Nanometers, 10 to the negative 9. So the difference, the absolute value of the difference would be 10 to the 9th here. So your nanometers cancel. Remember, anything on top multiplies, anything on the bottom divides. So that is going to be equal to 4.1 times 10 to the negative 7th meters. So I'm going to put this right here. 4.7 times 10 to the negative 7th meters. Alright, next I want frequency. Right now, all I have number-wise is just the wavelength. So we need an equation that links between frequency and wavelength. Remember, that is C is equal to lambda nu. C is the speed of light, if you remember. It's 3.00 times 10 to the 8th meters per second. That is equal to lambda nu. Now, lambda is the wavelength. So which wavelength would I use? Would I use the nanometers or would I use the meters? In this case, you would want to use the meters. The reason is because the speed of light is in meters per second, so that your meters cancel, and so you get the hertz, which are your correct units. So I'm going to plug in the value for the wavelength in meters. So 4.7 times 10 to the negative 7th meters times nu, which is my frequency. And if you solve for that, that should give you close to 7.3 times 10 to the 14 hertz, or 1 over seconds. I prefer 1 over seconds as opposed to hertz, because if you look at this, you can cancel the meters and you'd end up with 1 over seconds. So that makes more sense to me. So I'm going to put on my table here 7.3 times 10 to the 14, 1 over seconds. Alright, finally, I want to calculate the energy for this light that I saw, for this wave that I saw, wave of light. So right now I know its wavelength in meters and nanometers, and I know its frequency. I want to find the energy. So the way that I would do that is I would use the equation E equals H nu. So E is my energy, that's what I'm solving for. H is Planck's constant, 6.626 times 10 to the negative 34th joules times second. Nu is my frequency. I just calculated it. It's 7.3 times 10 to the 14, 1 over seconds. If you look at that 1 over seconds with seconds cancel, you end up with joules, which are the units for energy, so that should make sense. The answer I got is 4.8 times 10 to the negative 19 joules. Alright, now let's look at our numbers, see if they make sense. Well, let me go ahead and put this number here first. 4.8 times 10 to the negative 19 joules. So my wavelength is really small. It's 4.7 times 10 to the negative 7th of a meter. Remember, a meter is about a yard? So that's really, really small. Does that make sense? It should, because this is a wave of light. And so it should be very, very small. It's not something that we can see. What about frequency? Frequency, look at that number. It's a really big number. It's 7.3 times 10 to the 14th waves per second. Yeah, that should make sense because it's a wave of light, and so it should be traveling pretty fast and should have, you know, a lot of waves per second. All right, good. How about energy? It's 4.8 times 10 to the negative 19th of a joule. That's a really small number. Again, hopefully that should make sense because it's a wave of light. You know, we have lights around us all the time. You know, if they had a lot of energy, then, you know, we'd feel that. So it's a pretty small number, which should make sense. So hopefully now you should be able to do your worksheet for homework. When I come back on Monday, we're going to do a couple of fun labs with light and colors, and we'll do a couple of demos as well. All right, have a great day. See you on Monday.